For as long as we've had numbers, mathematicians have been fascinated with a particular type of whole number called a prime number. For those of you who can't remember what a prime number is, this should help. 6 is not prime because 6 equals 2 times 3. We can write 6 as the multiplication, which we maths nerds say product, of two smaller factors, 2 and 3. But let's look at 7. We can write 7 equals 1 times 7, but we can't break 7 down into the product of any smaller factors, apart from this trivial case of 1 and itself. This captures the definition of a prime number. A counting number, 2 or greater, is a prime number if its only factors are 1 and itself. And in case you're wondering, numbers like 6, which are not prime numbers, are called composite numbers. Now the primes begin 2, 3, not 4 because 4 is 2 times 2, but 5, not 6 because as we explained earlier it's 2 times 3, 7, then a bit of a gap, 11, 13, 17, 19, and off we go. How far can we go? Where do we stop on the way? Time to answer all that and more in this little primer on primes. Now perhaps you've already had a question about my list of the prime numbers, 2, 3, 5 and so on. But Adam, you may well be asking, why does this list begin at 2? Why does your definition only apply for counting numbers 2 and above? What about the number 1, which can be written as 1 times 1 and in no other way? Isn't 1 a prime number? Well, that's a fantastic question that I've just asked on your behalf. If you're confused as to why 1 isn't prime, you wouldn't be alone. Throughout history, there have been many great mathematicians who considered 1 a prime number. In fact, if you go back far enough, in many cases 1 wasn't even considered a number. It was more a building block out of which all other numbers were assembled. Well, these days, 1 is pretty much universally assumed to be a number, just not a prime number. And here's a couple of reasons why. For the definition of a prime number to have any meaning, it should be obvious that multiplying two primes together gives you a number that is not prime. Like our earlier example, where 2 times 3 gave us the composite number 6. But let's say 1 is a prime number, and so is 3, because it can only be written as 1 times 3. But if we assume 1 is prime, then 1 times 3 is the multiplication of two prime numbers, so 3 must be composite. So 3 is a prime number, and 1 times 3 equals 3, so 3 is composite. But 3 is prime, so 3 is composite. But so allowing 1 to be prime leads to a situation where 3 is both prime and composite at the same time. Don't know about you, I don't want to live in a universe like that. Here's a second reason that 1 is not prime in the unlikely event you're still not yet convinced. One important mathematical fact is known as the fundamental theorem of arithmetic. The theorem tells us that every whole number is either a prime or can be written as the product of primes, and importantly that these factorizations in a product of primes are unique. So 23 is prime, but 24 is 8 times 3, or 2 times 4 times 3, or 2 times 2 times 2 times 3. And there's no other way to factorize 24. You'll always get 3 2s and a 3 multiplying together. Well, let's say 1 was a prime number. You'll run into trouble. Let's take a simple example. We know 6 equals 2 times 3. But if 1 is prime, this is no longer a unique factorization of 6 into primes. Yes, 6 equals 2 times 3, but 6 equals 1 times 2 times 3. And 6 equals 1 times 1 times 2 times 3. And 6 equals 1 times 1 times 1 times 1 times 1 times 1 times 2 times 3. In fact, it should be obvious that we go from one unique factorization of 6 to an infinite number of different factorizations. So what seems to be such a little thing, come on, let's make 1 a prime number, it can't really hurt, leads us to a world of contradictions and mathematical messiness. I'm sorry, 1, you're a number, an awesomely important number, a number so special we even call you a unit, but you ain't no prime number. So we know the primes start at 2 and off they go, 2, 3, 5, 7, 11, 13, and so on. But do the primes ever stop? Is there a final, largest, supermassive prime out there? Turns out there isn't. We can prove it. The proof is, in my humble opinion, beautiful, and we owe thanks to one of the greatest mathematicians of the ancient world, a brilliant Greek mathematician called Euclid, who did his best work around 300 BC. Known as the father of geometry, the big E also gave us the first proof that there are an infinity of prime numbers. The essential idea behind Euclid's theorem can be seen in this argument. Let's say there's a finite list of all the primes. In fact, let's say the only prime numbers are 2, 3, and 5. We know that's not true, but let's pretend that it is, and we'll see what sort of trouble that causes. Let's take our list of all the prime numbers and let's create a new number. We're going to multiply all the primes we have together and then add 1. So 2 times 3 times 5 plus 1 is 31. Now, one of two things must happen here. Either this new number 31 is a prime number, so our list of primes was not complete. Or if 31 is not prime, then it must have factors. Well, let's try and find them. Clearly, 2 is not a factor of 31. It's obvious that 2 divides into 2 times 3 times 5, but 31 is only one more than that. We can't squeeze in another multiple of 2, so 2 is not a factor of 31. But it's equally clear that 3 doesn't divide into 31 by exactly the same argument. It divides into the 2 times 3 times 5, but 31 is only one more. And following exactly the same logic, 5 does not divide into 31. So as we said earlier, 31 is either prime or it has prime factors. But if it has factors, we've shown that none of the primes we had, 2, 3, or 5, are factors of 31. So what we assume to be our complete list of all the prime numbers can't be complete. There must be another prime, in this case either 31 or primes that are factors of 31. Now, if we'd assume there were more than just 3 primes, if we'd written a list of 20 primes or 50 or 5,000, however many you allowed, if we write a finite list, we can just go back and do the same party trick again. Just multiply all 5,000 primes together and add 1. We get a massive number, but the argument's exactly the same. Either this new number is prime or it must have a factor that's not on our original list. We can never write a complete finite list of the primes. Thank you, Euclid. The primes must be infinite. So thanks to Euclid, we know the primes are infinite. And we know where they start, 2, 3, 5, 7, and so on. So there must be at any given time a largest prime number that we know of. Indeed there is. And the story of the exploration of the largest prime known at a given time is a rollicking adventure. There is one tiny bit of primary school mathematics we need to refresh in our minds before we race off on this quest. Remember back in about year 5 or 6 when numbers got a bit weird and started floating up in the air? We saw things like this, for example. 2 with a 3 next to it. 2 cubed, remember that? That crazy 3 floating here isn't any sort of new number or any collapse of order in the universe. No. It's just a piece of mathematical notation. A shorthand way of representing 3 2s all multiplied together.
Hate to interrupt. Would you prefer uninterrupted indulgence? Head to findqualia.com to access the entire series by comedian, broadcaster, and mathematician Adam Spencer, completely ad-free.
So this thing we see here, which we pronounce as 2 to the power of 7, well, represents this. 2 times 2 times 2 times 2 times 2 times 2 times 2. 7 2s multiplied together. Now, for reasons that I won't go fully into here, the vast bulk of the biggest primes we've ever detected are of the form 2 raised to the power of some massive prime number, take away 1. Using the first few prime numbers as powers yields prime answers. 2 squared minus 1 equals 3 is prime. 2 cubed minus 1 is 7. 2 to the 5 minus 1 is 31. 2 to the 7 minus 1 is 127. And I can still remember the sense of excitement I had as a young maths nerd when I spotted the above pattern and thought, wow, I've discovered something new. 2 raised to a prime power minus 1 is always prime. I also remember the sense of crushing disillusionment I encountered when I realised the next prime power, 2 to the 11 take away 1, is 2047. And you don't need me to tell you, that's 23 times 89. So 2 to a prime power minus 1 doesn't always give us a prime answer, but it has furnished most of the mega massive primes we have ever discovered. Suffice to say, there is a beautiful mathematical shortcut to testing whether a number like this is prime. We don't have to try and divide it by 2, then divide it by 3, then divide it by 5 and 7 and so on, which for numbers the size of which we're talking about would take far too long to be practical. For any coding junkies out there, the test for primacy for numbers of the form 2 to the power of a prime number, e take away 1, has an incredibly simple programming structure equivalent in your language of choice to this. Currently, the largest prime we know is, brace yourself, it's simple really, just write down the number 2, 82,589,933 times, multiply them all together and subtract 1. Discovered in December of 2018 by 35-year-old American IT professional, Patrick LaRouche, it is 24,862,048 digits long. And we know it's prime as confidently as we know the number 7 is prime. LaRouche was using software provided by the GIMPS project, the great internet Mersenne prime search, which runs in the background of any computer and tests candidate prime numbers as part of a giant international search project hunting out mega primes. If you'd like to take a shot at international math stardom, why don't you visit GIMPS today and get searching? Now, one final little tidbit about the primes, and something that really blows my mind. For all the fascination we have with prime numbers, and we've had over the years, we know in many ways decidedly little about them. Testing if a given massive number is prime is a laborious process. Given a large number which we know is prime, determining the nearest prime number to that is often effectively impossible. We know very little about how the primes are arranged out through the infinity of counting numbers, of what patterns or rules, if any, they follow. But one thing we do know about patterns within the primes is due in a large part to the work of the brilliant Australian mathematician Terence Tao. Let me explain. Look at the prime numbers 3, 7 and 11. Not only are they all prime, but they're also separated by the same amount, namely 4. Start with 3, add 4 to get 7. Add another 4 to get 11. We keep going from 11, we get to 15, which is 3 times 5 and not prime. So we have a chain of prime numbers with 3 members, and they're separated by a distance of 4. The fancy mathematics speak for that is to describe 3, 7 and 11 as an arithmetic progression with an initial value 3 and a common difference of 4. So similarly, the chain of primes 5, 11, 17, 23, 29 forms an arithmetic progression starting at 5 with a common difference of 6. When it comes to finding longer progressions, we quickly need the help of computers. There's only so much you can do with pen and paper, especially given how hard it is to test whether large numbers are prime or not. But the longest arithmetic progression of primes, of which we are currently aware, was discovered on the 23rd of September 2019 by Irishman Rob Gahan, who found out that by starting at and advancing by each time, you have an arithmetic progression of 27 primes. Yes, thanks to Rob, we know that starting at 224 quadrillion, 584 trillion, 605 billion, 939 million, 537,911, and increasing by 18 quadrillion, 135 trillion, 696 billion, 597,948,930 each time, we find a chain of 27 prime numbers, ending just shy of 700 quadrillion. Now, these are fantastically large numbers, and your mind might already be slightly boggled. But get this. Terence Tao and his good friend Englishman Brian Greene made a wonderful piece of mathematical discovery known not surprisingly as the Greene-Tao theorem. Tao and Greene showed however large a whole number you choose, there has to be an arithmetic progression of primes of that length somewhere out there in the infinity of all counting numbers. Yep. Given all the grunt of modern computing, the longest progression we've currently found is 27 primes long. But if you want a chain of 30 primes, according to the Greene-Tao theorem, it has to be out there somewhere. 50 primes, out there. 100 primes, out there. A chain of 1 million, 1 billion, 1 trillion. Yes, yes, yes. Remember the largest prime number yet discovered? Well, out there in the endless expanse of counting numbers, there has to be a chain of prime numbers in arithmetic progression with that many members. Now, the Greene-Tao theorem doesn't show us how to find any given progression of primes. It merely proves that for any required length, one must exist. But for mine, this insight is just so unbelievable, so beautiful, so deep. Take a bow, Terry Tao. You rock.